But I actually just learned some new things about how surface plasmon resonance works. So I want to pass that on to you. I found a couple of good literature things that explained it in new ways, and so I'll be showing you some of that. Really what this is for when somebody comes up to your poster and they ask you, what are you doing this for? Well, you're going to try to measure antibody binding to the fragments with surface plasmon resonance. Well, you need to have some way of explaining what that means. And by the way, 3410 students, this is also going to be, there's going to be 1 or 2 questions on test 1. And again, you choose which questions you answer, but you have the opportunity to turn this into 2 test questions, 20 points on test day. And the idea is basically explain back to me these physical chemistry things. How does surface plasmon resonance work? It's a great physical chemistry question because it involves up to relativity, if you really want to go there. There's a lot of physics in this. And a lot of people don't know what's going on with it because it's a relatively obscure corner of physics, but it's very useful. And so we start with the question of, why is gold yellow? And by the way, this is a bit of an approximation, but it's certainly involved somehow with the fact that gold has surface plasmons that resonate with light, okay? This is actually a bit wrong, but it will be right enough for anybody who's talking to you about your poster. And it has the right foundation. That's what we want. So here are the concepts that you want to get to. And this is all in order. We're going to start talking about light and the refraction of light. Did you ever do anything in physics with the refraction of light? Do you do like experiments with things like that? Does anybody remember an exact thing that you did with refraction in physics? Do you ever do equations about the angle of refraction maybe? Or refractive index? Yeah, so you sort of dealt with that. We're going to talk about what refractive index is. So refraction actually leads to, in a certain case, it leads to reflection. Total internal reflection is the type of reflection that happens under a special case, a special angle of refraction. And the total internal reflection, the light wave extends below the surface or below the interface at which the reflection is taking place. At that surface, we also put a piece of gold. And the gold has surface plasmons that interact with light. So the third component, you have a piece of gold, you have an interface between 2 refractive indices, piece of gold at the interface, and then you have a laser shining on it. The laser is a red source of light. And it turns out that light and the gold electrons have a special energy level that can resonate and interact. So when the light's energy reflects off a metal surface and it matches the plasmon's energy, resonance occurs, and there's a shadow that appears. The light energy actually disappears. Now you know from the first law it's not created or destroyed. It actually is moved into a different form by resonance. But to us, effectively, the light is gone. There's a shadow there when we look at it. So that's all the concepts that we wanted to go through. So number 1, light refracts. When it moves through a medium, when it has to be a clear medium for it to move through it, and then it will move differently. So this is a picture of Venus's transit across the sun. And you can see that Venus has a pretty thick atmosphere because you see the light actually moving through the atmosphere, and it's being bent by the atmosphere. The light's coming from the sun, but it clearly has been bent from its source by the atmosphere, refracting. The light is like coming, it hits the planet and it bends through the atmosphere. That is refraction. And so the atmosphere is very thick. It's also transparent enough to light. The light passes through it, but the thick atmosphere bends light. Here's another picture. This is not Photoshopped as far as I'm aware. At least I think it's reasonable that it could not be Photoshopped. This is, I think this might be Yellowstone or something. It looks like Yellowstone to me. I don't know if anybody recognizes it for sure, but we'll say it's Yellowstone, okay? But here's a moon set or moon rise. And here is a person, and you see that the moon's light, which is reflecting the sun's light, is refracting through the water. The water is acting like Venus's atmosphere and is bending the light. So refraction and reflection are actually related phenomena. The previous thing was reflection off the moon and then refraction through the waterfall. But here's another way of, at a certain point, refraction becomes reflection. If you look here, you're looking up from under a pool, and you can see through the pool into the atmosphere, different refractive indices for these. But when you look at a certain angle, the light starts to reflect back at you. It starts to act like a mirror. And in fact, you can even see it's sort of circular from your standpoint. It's based on the point of the viewer, and it's based on a certain angle. Once you get above this angle, you just have regular refraction. You know the light is bending somehow. And actually, if you look at where this is, you'll see that the light has actually been bent coming to you. And in fact, if you look at the way the refraction works, the refraction is bending the light down. That window is actually supposed to be really up there, but it looks like it's down because the light is being bent down. Okay, well that makes sense. The light bends when it gets to certain interfaces, and that would be refraction. But the light bends down. What happens when the light bends all the way down so that it's parallel to the surface of the water? Then it can't refract anymore. It can't leave the medium. Once it reaches that angle, what it does is it gets bent so much that it's bent inside the original index, and it's reflected rather than refracted. It's all a measure of the angle. The angle of the light reaches this critical angle, and then it starts to reflect rather than refract, because it can't refract anymore. It's not possible for it to be bent because it gets bent back into the original surface, basically. They are similar phenomena. Here's an example of this is total internal reflection. You see this is not a mirrored surface, but this is just a blue light coming in at an angle. And you can even see, if you look carefully, this light is being bent. It's coming in at this sort of angle, but then it's bent down more. And I believe this is a blue laser. You see it spread out a little bit by the thing, but it mostly stays in the same place. And then it bounces off the interface. So this is a case where there's total internal reflection going on at the interface. That means that something clear that has a thick refractive index can actually reflect light. And so an extremely high refractive index, that would be diamond. This is the whole idea here, the physics behind this, is that the light bounces around inside the diamond, and it's trapped inside the carbon matrix. The diamond has a refractive index of 2.4, which is really big. All refractive indices must be 1 or greater. And but usually you see something like 1.3. We have water on the next one. Water was 1.3. This is a lot higher than 1.3. And in fact, it's one of the highest refractive indices you can have. Again, diamond is actually a pretty chemically special material. We've talked about its heat capacity before. And now it has a special refractive index, all because it has an extremely rigid and dense matrix. Small atoms bound together very tight, and they really can't move much without their neighbor moving. So cubic zirconias, if you make a clear thing with a high refractive index, the reason why cubic zirconias can fool casual observers into thinking they're diamonds, they sparkle like diamonds because the light internally refracts and reflects inside them from their high refractive index. And the high refractive index means two things. It means the angle is steep, at which the angle at which you have refraction is steep, and therefore it's easier to get internal reflection, because it's a steeper angle means it's easier to get. The other thing about refractive index is it actually changes the speed of light. Now, physics people, does that bother you? If I say the speed of light is changed, am I lying to you? I mean, where have you heard the speed of light doesn't change? That's actually one of the axioms of a certain area of physics. I don't know if anybody took capstone in fall, but Dr. Lindbergh always talks about this. Who was the scientist who really established that the speed of light, he didn't establish that the speed of light doesn't change. He did establish that the speed of light under a certain condition is constant, and the fastest thing, nothing can be faster than light. Anybody want to guess which oh, I started to say it.
Einstein?
Yeah, it was Einstein. Einstein established that nothing can be faster than light, and that the speed of light is constant no matter what your reference frame is. And that has lots of implications. That's all the implications of relativity. So if Einstein made his name by saying that the speed of light, nothing can go faster than the speed of light, how in the world can I say that the speed of light can itself change? Anybody, any idea how there was one specific thing that Einstein always said about light? The speed of light does not change, ... Under which conditions? No matter how you're moving, it doesn't change. How can you slow down light? If you pass it through a diamond.
Vacuum to the air.
Yeah. Well, if the light bending is actually a consequence of the speed of light slowing down. So Einstein said, speed of light is a constant in a vacuum. But of course, light can interact with matter. That's the whole thing about mirrors, how they work. So the direction of light can be changed by a mirror, and actually the speed of light can be changed by the medium. It's just, it can only slow down. You're not going to get something that's going to actually speed up light. So that's the whole thing about, so the speed of light has to do with refraction. You always have a thick, clear material when you're changing the refractive index. This is another thing, another video from the Exploratorium. You can tell because it has the Golden Gate. And you see in real life, you have these broken lines, but when you put the thing at the right angle, the light actually bends. And you see right here, you have the light bending when it enters and light bending when it leaves. And it appears like the broken line, this is what's actually printed, but you actually are bending the light. When you put this at the right angle, you have the light bend so that the light is bent to make the bridge appear unbroken. And that is what refractive index is. That's because the light is going slower. Because of light's properties, because of light's invariant velocity in vacuum, when it hits a medium that slows it down, that means that its angle changes. And that's kind of a weird thing until you look at it a certain way. You have to look at it with calculus to really understand why does light bend when it slows down, okay? So the refractive index is defined as the speed of light in a vacuum compared to the speed of light in the material. And so the speed of light in the vacuum, the refractive index of water is 1.332. Did he put this right? Did he have this upside down? Yeah, the speed of light in the material is slower, so it's smaller, and you end up with a number bigger than 1, okay? So a diamond will slow light down by about half its velocity if you think about its refractive index of 2.4. So the speed of light in a vacuum is 1.33 times faster than the speed of light in water. Or it's probably more accurate to say light goes through water more slowly because you don't want to talk about light speeding up. Because look at that rightly, light cannot speed up. Nothing can go faster. And this is how the calculus for it works, okay? A light ray always takes the fastest path possible. And so when light is moving, say, from a thicker medium to a thinner medium, it's like a hiker going down from above the snow line to below the snow line. Let's say the hiker's at point A in the snow, and the hiker is hiking down to point B outside the snow. And maybe you've encountered this, especially like in Florida. I don't have much experience with the snow, but I do have experience with like waist-deep water, which will really slow you down. And so if you're getting out of the pool, if you need to get from point A in the pool to point B outside the pool, it's actually not fastest to go directly from point A to point B because you spend more time in the pool and that slows you down more, right? But also it's not fastest to simply go straight out of the pool and then to walk because, assuming you're at constant velocity for all these things, that you're not like speeding up unfairly. If you do that, that's too much distance. There's actually this is not the fastest way, neither of these is the fastest way to get from point A to point B. Instead, the fastest way is something in between that has sort of the best of both worlds. It's a compromise between distance and slowness of speed, the medium slowing you down. And you can actually calculate what that is. You could actually do this calculation with calculus, because what you do is you set up an equation where you say, okay, the distance of my angle is going to be x, and x can be anywhere between here and there, and I know that here and here are sort of maxima, and it will improve to some point x. I want to find the best point x for the total travel time t to be minimized. And you can see right now why this is like the delta G type equations that we're talking about. The system, the light is a system that could take any path. It takes the path that minimizes its total travel time. Interesting about why it does that and what it means by the way this writer described it is that nature somehow knows calculus. I prefer to think of it as calculus expresses what nature is in a good way, so I put it backwards from what they say. It's not like the light is a little computer. The light is just light. It's made to be, it's made to take the fastest path possible. And so the question of how it knows that is actually a very interesting philosophical question, but the fact that we can calculate it, if we can find the minimum, we know what light will do. So this, and realize that if you think of this as a light ray, the light ray will take the minimum path, and that means the light ray will bend. When it goes from a thicker medium to a thinner medium, it will bend down like this. And so you can even measure this, and someday I actually think I might buy a couple of these handheld refractometers that will actually measure the refractive index of a solution. So you put the solution on it, and you look through it, and I don't even know exactly how it works because I haven't looked into it, but you see a line where the refractive index is. And you see right here, refractive index of 1.3 is water, and you can compare it to methanol, I believe. Methanol has a higher refractive index, so you can see how methanol and water mix. And what's interesting is, this is 100% water. This is a graph where you measure the refractive index of 100% water. You see it's 1.33, like we said. And actually, the refractive index of methanol is actually lower than water, slightly. So light will actually travel a bit faster through water, if I have that right, faster than methanol than water. It'll be different, okay? So the refractive indices are different. And so you would expect if you mix if you mix water and methanol to a 50-50 ratio, you'd expect a point about right here, right? The refractive index should be on a line between the two. Well, lo and behold, and we're going to talk about this in physical chemistry actually on tomorrow, it doesn't always behave linearly. In fact, sometimes you see what's called, I believe this is called hysteresis. Basically, it's nonlinear behavior. And you measure, the mixture actually has a high refractive index up here. And it follows a nice curved line if you do the different mixtures of water and methanol. So, ideal behavior, some systems will actually give you a line when you mix them. They will mix according to what the line would predict. This one, however, doesn't. Where is that coming from? Is our refractometer wrong? Things like that. We will talk about all this tomorrow. When we do, I just want you to remember that we could measure this with refractive index, and we could explain this with those equations. That gets us to physical chemistry too far, but I just want to say this is coming. The main thing is you can measure refractive index, and when you have a water interface with something else, it's going to bend light. and it's going to have a refractive index there. And this is what's inside the BIAcore, okay? BIAcore uses actually a situation of total internal reflection. They have a water on top, and they have a prism on the bottom. And by the way, top and bottom might be flipped around sometimes, so be ready for that. But if you have the light at this angle, the light will be refracted, great. But if I keep moving this angle up, this angle moves down, right? And when I get to the angle where this angle, it can't bend anymore and still be in the water, it will bend and it will be in the prism. So it will become a total internal reflection. You have to move the angle up. And then you get to the point where the bending goes back down into the original material. So that's very cool, but it's dependent on the properties of the water. The fact is that the light is reflecting off of the water because of the water's refractive index. And this actually makes all the difference eventually. So this is the case of total internal reflection. In the BIAcore, it's a red laser that does this, and it's at a constant angle. You don't even really see the angle. It's just in how it measures it. It gives you it in units. But the really important thing is the units BIAcore gives you is actually related to the refractive index of what's in the water. And so you just put different stuff in the water and you can measure its refractive index. So realize that the light is sampling because it's reflecting off the interface. The light beam is reflecting, but it actually is interacting with the medium at that point. Okay. The other thing that happens, and this is going to be weird at first, and it's still weird when you get around to it, but the other thing at that interface is not just a prism water interface. There is a gold layer at that chip. Now, gold can be very, very thin and still be gold. It's good. But the other reason why we use gold is because gold has plasmons at a very specific frequency that will interact with the red light falling onto them. So you probably never, tell me if you've talked about plasmons in physics. Probably not. I don't know if I ever heard the word when I was growing up. But what a plasmon is a group of electrons that moves as a single unit. You probably heard of the electron sea inside metals. Have you ever heard that? Or, metals are a lattice of nuclei, and then what's happening to the electrons? How would you describe what the electrons are doing within a metal? That explains why metals are so conductive. How have you heard that described in your chemistry classes when you talked about electrons in bulk metals, like a metal wire or whatever? Yeah, so they flow freely. It's a fluid metaphor, right? You talk about them like they're a liquid. There's a current, which we also use for a liquid. And it's not really a liquid. It's not like you shake the wire and electrons fall out. So there's some ways in which it's not like a fluid. But it's really important to look at these metaphors that we have and realize that even current is a liquid type of metaphor. The reason is the electrons sort of behave like a liquid. They stay in their container and they move, they can flow through the metal. That's why they conduct. Well, it turns out that those electrons can sort of oscillate together. They have waves. And so a bunch of them can have their waves all aligned, and those will act differently than electrons that don't have their waves aligned. And when they move together, we call that a plasmon. Basically, if we can have an oscillation of a group of electrons that moves as one, then we can treat that as a single thing, not really a particle, but we call it part of a plasma. By the way, what's the other place you might, if somebody says there's 3 phases of matter, have you heard of there's 4 phases of matter? Because there's gas, liquid, solid, and plasma. But we never talk about plasma. Do you know where plasma can be most often found and at least seen, maybe not touched in our world? What's that? Exactly. So the fusion reaction produces such high temperatures that you actually move beyond our little paltry earthbound phase diagrams. and you actually get to a state where the electrons are not associated with individual nuclei at all. And that is called a plasma in the heart of the sun. Well, in metals, not all the electrons are like this, but there's a certain layer of electrons in metals that are also not tied down to original nuclei. And it is accurate to call it a plasma. Usually when you think plasma, you think like Star Trek, or I think technically the planet Naboo on the first Star Wars movie. Do you know why everyone cared so much about that stupid planet? Because they had a whole war over it, right? They never explained this in the movie. According to Star Wars lore, Naboo's core is made of plasma. And that's a resource that they need, everyone needs to get it. And that's why when, at the end of Star Wars 1, what's the battle that happens at the end of Star Wars 1? I hope this isn't a spoiler. Where does the lightsaber battle take place? It's this weird place with all these like jets and things like that. That's the plasma. So Lucas was trying to say that, but he forgot about mentioning this whole thing about why are people fighting over Naboo in the first place, even though he had it in the set design. So anyways, plasma is something that they always talk about in Star Trek. There's no such thing as a planet with a core of plasma, but in a sense, metals have tiny little plasmas in them, low energy plasmas, okay? So the thing is, these are oscillating as a unit. When they oscillate in a certain movement with their charge, they actually can match the oscillation of the electric field of light. All light is electromagnetic radiation. It has a magnetic moment and an electric field associated with it. And so the thing is that the electric field of light can match the oscillations of the electrons, the energy level of each. If that happens, then you have the energy can move through those levels, and you can have transfer of energy from the light to the oscillations of electrons. This is resonance. And this is what the resonance in surface plasmon resonance is. Now, actually, you can have amplification or cancellation depending on how the waves are lined up. In our case, we actually have cancellation, because you end up with the light bounces off the surface and it creates a shadow because some of the energy of the light is moved into the metal, into the creation of surface plasmons. So most metal plasmons, most metals have a plasma inside them, right? Most metal plasmons will actually do resonate with some light, but they don't resonate with visible wavelengths. So they reflect all visible light, and that's why if you see my microphone right here, most metals are silvery. In fact, if you look at one of those things that says periodic table, and here's a sample of all the periodic table elements, most of the metals are just boring. They're silver. You can't really tell by looking at them. That's because they are reflecting all visible light. But gold and copper are different, right? Gold and copper actually have different energy levels, and these are different energy levels of plasmons that will actually interact with the visible light. Therefore, they end up colored, because the gold will reflect just yellow, and it will absorb non-yellow colors. Copper will absorb everything but reddish yellow. And so the fact that gold and copper are weirdly colored also means that they have certain visible light plasma electron energies. By the way, these are not actually the electron energies that we're using in surface plasmon resonance. There are other levels that we're using. So you shouldn't say that it's exactly what's going on, but it gives an example for why gold is special. So this color right here is the color of reflected yellow light. The other ones are absorbed by some sort of plasmon resonance with visible light. So here's a really good explanation. Now, plasmas are most easily occur in copper, silver, and gold, and they also occur in magnesium and aluminum and alkali metals. Basically, if you have electron Cs, you will have a plasma. The question is what its energy level is going to be. You can calculate the plasmons in a bulk metal according to this equation. And I have to show this to you guys because it is a physical chemistry equation. Basically, you have N being the number density of electrons, and then you have E is the charge on an electron. How many electrons do you have? Times the charge of an electron squared, divided by the dielectric constant of a vacuum. By the way, we're going to see this again in chapter 11. So you just want to remember this. I'm not going to ask you to calculate anything with this, but in chapter 11, we're actually going to have we're going to talk about calculating how electrons work. The equations are going to look just like this. So, but it just includes charge of the electron, dielectric constant, and then the mass of the electron. So charge, mass, number, and then some proportionality constant. You square one, and then you take the square root to get the frequency of the oscillations. You can calculate this. Now this is true for the inside of the metal. It's actually slightly different at the surface, but I think it's just like divided by 2 or something. And the main thing is, each metal will have these oscillations in it where you have these electrons sort of grouping up into plasmons. And there's an electric field of the plasmons. When light shines on it, there's an electric field that the light has. When these match, you have resonance. By the way, if you have somebody from physics who wants to talk about this and you can explain any part of this, honestly, they should be pretty impressed. That's what I want you to think about as you go through this. Okay, so an analogy that describes surface plasmons is if you have seaweed in water during near a shoreline. So it's like the shoreline is the interface, like the surface of the surface, the electron sea is like the regular sea here. And the plasmons are a little bit like, if you think of seaweed floating in the water at the edge of the sea, basically as it sloshed back and forth by the waves, it's going to slosh back and forth according to the way that the waves are pushing it. And that's the idea, that you have the surface plasmons that can interact, and the sloshing back and forth can match the sloshing back and forth of light. That's when you have resonance. The final thing about light is that, because remember, the light is reflecting off of an interface, and we said that the light knows the refractive index of the medium that it's reflecting off of. The quantum mechanical way to talk about this is to say the light actually sets up an evanescent wave. In a sense, because of the quantum mechanics of it, the light actually sets up a wave-like behavior that extends into the thicker medium. So it extends into here, and it actually, you can calculate, it extends by half the wavelength of light. Well, guess what? We use a red laser. The red laser has a long wavelength. It's the longest easily available wavelength that you can get. And so the long wavelength means that we can see deeper into the water. And that's, I think, one of the reasons why they use red and not green lasers in BIAcore. Also, red are a lot cheaper. That doesn't hurt. Okay, so you can see a little ways, but only a little ways, only half a red wavelength you can see into the other side. But that's all you need, because you have a gold layer here. You can put stuff on that gold layer, and the light will measure its refractive index. And here's the final key to it. Refractive index of carbon is very different than refractive index of water. If you have carbon mass binding to this surface within the evanescent wave, then it will actually change the refractive index, and you will see the refractive index change, and the properties of the light reflecting off that refractive index will also change. Basically, when these two levels match, you have resonance. You have a shadow in this light that comes from the refractive index of that medium. And that refractive index can change when, for example, you have a protein fragment on this side, and you have an antibody coming up, and the antibody binds. Mass has changed, refractive index has changed, a shadow appears, or actually the angle of the shadow changes that is reflecting off of this, and the shadow is caused by resonance. Okay? It's a lot of stuff, but this is why I'm doing a lecture on it, so that you can summarize it to other people in writing on your poster, and also when people talk to you about your poster. So I do want you to sort of go out of your way to explain this to people as appropriate, because it's part of the class. So when you have the total reflected light, you have this reflecting off of it. The light energy, this is actually a misstatement. It's not lost, it's changed, but it's lost from the beam. It's changed from light into something else. And so you have the shadow, and you have the shadow occurring at a particular angle that is dependent on the refractive index of this medium in the water over there. So you put stuff on the chip, and you measure whether mass approaches that side of the chip. The cool thing about this is you don't need to do anything else other than attach something to the chip. You don't need to do anything to the antibody that's being flowed through the water, because all it needs to do, it needs to have mass, and then it needs to bind. The other thing to be aware of is this changes when the refractive index changes. If you change the buffer, if you change the salt concentration, you also will be changing the refractive index of that solution. So when you see a change in BIAcore, you've got to run the proper controls, run the proper subtractions to be sure that the change is coming from the actual change in mass and not just the change in buffer salt concentration. But there are ways to do that. So this is just another view of it. The quantum mechanical nature of the wave means you have the evanescent wave which extends into the solvent, and it's technically on the other side from the reflection. And the gold layer is so thin that it doesn't take up too much of that, that wavelength that you have. You have a certain amount of space that it will extend into the solvent. Okay? So that's, you can think of the evanescent wave as extending down into here. And actually, so the evanescent wave is here and it's extending down. And what's shown right here is more like the surface plasmons oscillating, the wave of the surface plasmons. So there's lots of waves right there. So because it's affected by the refractive index on the other side of the interface, when something sticks to the other side, it changes the mass, changes the refractive index, changes the angle of shadow, and you end up with the signal that you can measure in real time. Okay. This is just one more way. I took these. They're trying to explain things to people who use BIAcore, but honestly, after you've been through this, we're going into more detail than most of the people who use BIAcore. So the easiest way to detect changes in the light reflecting is to use a prism to sort of make the light focus, and then it spreads it out again. Then you have the shadow that shows up, and the shadow will move depending on if something binds here. So why is gold special like this? Well, gold is the only yellow metal that's that big, you know. Nothing else really looks like gold. And so gold has special properties. It's also very big, right? It's at the bottom of the periodic table. And some people are like, why is gold so unique? One of the explanations is, if you calculate how fast the gold's electrons are going, remember from quantum mechanics that you have the electrons are being drawn in by the nucleus. If you calculate how fast they're actually going, they travel at a substantial fraction of the speed of light. There are so many protons pulling on them that they actually pull them through the speed of light, and they approach the speed of light, and that means their mass changes. That means that, remember what we said about relativity? It's actually it might be the explanation for why gold has special chemistry, and also why lead, which is right next to gold on the periodic table, it's also a very big nucleus. It also has relativistic electrons that will have greater masses, apparently, because our reference frame is much slower than their reference frame. It's kind of crazy that something like relativity, and by the way, this is a joke. This is basically they're throwing everything in, and I just want to say, oh, this makes it really easy and clear, and they basically throw in a bunch of confusing things together. But the confusing thing that they throw in together is also entropy. Okay, so there are certain ways in which you can ask, why is gold special, why is lead special? And if they're at the bottom of the periodic table, it's possible it could be because of that. So basically that's surface plasmon resonance. You measure mass changes through refractive index changes, and there's different brands of this. There's another one called Octet. There's a couple other ones, they come and go, but BIAcore was the first. It's the one I learned. It's the one I have. I bought one a long time ago, and I bought it cheap from the UK. So it actually is rated to run on 220 volts rather than 110 or whatever the way is. It's actually a UK instrument. And so it's weird, but I'll teach you how to use it. And SPR is probably the major use of plasmons. But there are some other ways that plasmons are used in science. There's a phenomenon called extraordinary transmission. If I have a screen and I shine a light through it, the screen blocks the light, right? Well, not if the screen is made with a certain metal and with holes of a certain size. Because in certain cases, the surface plasmons will actually amplify the light. They're even not 100% sure how. They have a vague idea. But it will actually amplify the light shining through a screen. That's weird. That's because of plasmons. And there's a scanning near-field optical microscopy that actually scans. It has a glass fiber, and it will actually go over a metal surface, and you can have it induce little plasmons. And the plasmons will ripple out from the place where you're inducing them, like raindrops falling on cement or something like that. You can actually see them like rippling out. And then some people are saying, actually, information in microprocessors and regular metals travels at like 10 to the 5th below the speed of light. This actually might be a case where we can use plasmons to travel closer to the speed of light, which might mean faster microprocessors. There's some problems with that, but yeah, we don't know. The main thing for physical chemistry is you're basically you're having light plus metal, and it produces special kinds of electrons that can move in special ways. If you can move in special ways, force times distance, that means you can do work. And this is literally a case where surface plasmons induced by light, photons will hit this nanoparticle, and they'll produce electrons, which will produce a current in this cadmium over here. And you can see the electrons are moving. This is the definition, physical chemistry definition of work. We can do it with proteins too. There are people who have done an experiment where they've put proteins on a metal particle. When you shine a light on them, it creates these plasmon energetic electrons. And that can create an increase in temperature, or it can supply electrons that can make the enzyme work differently, maybe work better. So this is a light-driven, basically if you shine a light on something, you can affect the electrons, and you can have the resonance that can either amplify or cancel out. So I think that's enough physics for you, probably. I think I've justified the physical part of physical chemistry. Then I want to go through to SPR, but because I've been going on for a little while, why don't we take